In this video, we're going to discuss real gases rather than ideal gases. Ideal gas law, PV equals nRT, works for any gas. Doesn't matter the species, we say they all behave the same. So it doesn't matter what you have, if you have a container of a certain size and there's so many moles of gas in there, at a certain temp it will give you a specific pressure. Reality is, this is close, but not perfectly true. You'll get a very slightly different real pressure for the same moles in the same volume at the same temp. So how do we distinguish those? Most of the time it isn't necessary to. If you are anywhere near realistic human on Earth quantities of pressure and temperature, this will never be necessary. The ideal gas law is extremely good for things that are at anywhere near 1 atmosphere and anywhere near our normal temperatures. But if we think about those gases, we draw them as little points, but they're not really. They have a size. If I tell you this container is 1 liter in volume, well, if I had the same container, but I had filled it with some water, and we had gas above it, and I ask you what's the volume of the gases, well, the gases aren't in the water. At least they're not being a gas if they are. They're in the space that isn't occupied by the liquid. Well, the truth is, even if you don't have a liquid, I have some particles. Gases do take up a very tiny volume. As far as any one of our gases is concerned, it can't take up that space. This particle cannot be where the second particle is. It'll bounce off. So the available volume in our container is the container minus the volume of the actual molecule. Now, normally that's so tiny we wouldn't consider it, but it's still a consideration if you want to be extremely exact. And it's especially a consideration if you start having a lot of gas around. If you have enough gas particles, the reality is they start occupying a fair percentage of the volume, which means your real volume to bounce around in is significantly less because there's always going to be some gas in your way. Additionally, particles are supposed to just bounce. If I've got my particles, they're supposed to just bounce, hit the walls and bounce, and keep bouncing. If they hit a particle, they'll bounce. That is all they're supposed to do. Ideal gas law assumes that the particles do nothing but bounce into each other. But if you have, say, water, well, water has a partially negative end. That oxygen atom is far more electronegative. It steals the electrons from the hydrogen. Those hydrogens are somewhat positive. As a result, there's some attraction. There's like magnets. There's a positive and a negative end. As two waters get near each other, well, they can be drawn towards each other. The net effect is if I have two particles in a container, ideally, they will drift right past each other. They won't care that the other one is there. But the reality is, as they get near each other, so they'll follow their path for a while. But as they get near each other and they start to interact slightly, they'll end up pulling towards each other. They might not hit, but that attractive force, if you slide one magnet past another one on a table very quickly, they might not stick together, but they might move the second magnet even if they never touch. The net result then is that your particle takes a different path as it is bouncing around to go on to hit the walls. Now they'll eventually hit the walls, but a straight line is a shorter distance than a curved line. Well, it's a little hard to see with only one example. On average, because of these curves, it takes longer to hit the wall. If it takes longer to hit the wall, you don't hit as often. If you don't hit the wall as often, you don't exert as much pressure. The attractive forces between molecules results in lowering the pressure, simply because it creates longer paths for our particles to travel than the ideal gas law presumes. How do you take these into account? Well, there's a nice set of equations, the van der Waals equations. Van der Waals looked into it and basically came up with an equation that said my pressure plus my moles of gas squared, since they have to interact with each other, the amount. You need two of them to come together, so they multiply each other. So n squared moles times A divided by volume squared. Continuing, our second bit, our volume minus our moles times B. All that has to equal nRT. Van der Waals modified the pressure and volume calculations. What's happening if we think about the volume? Well, the volume of my container might be 1 liter, but my gases take up a size, so real volume. The available volume for the gases to bounce around in will be the container minus the size of the actual molecules. So the number of molecules times its size. If you want an example here, helium has a B value of 0.0237 liters per mole. They just take up a little space. The volume of the mole of atoms takes up a tiny percentage of that total volume. Helium also has an A value. So helium's A value is 0.034, and the units are atmospheres liters squared per mole squared. What's happening with the A value, if we go and look at our pressure component? Well, pressure is going to be modified based on its ability to interact with other things. The more particles there are, the more they will interact. The space they have to spread out in will determine how often they can interact. So we see the volume is actually part of our pressure modifier. And A is a measure of how interactive the molecules of gas are. The greater the forces between the molecules, the larger A will be. For an example, water has an A value of 5.46 and a B value of 0.0305. Water is a little bit bigger than helium, but what's most significant is that water has a great charge attraction. Water has an immense attraction to other waters, where helium, being just a single free-floating atom, doesn't have any charge on it, and so it doesn't have almost any attraction to nearby atoms. These components can be combined in order to calculate out your actual values. So if we want to find our real pressure here, let's do an example. We're going to be in a 1 liter container. We're going to be at 273 Kelvin. And we're going to have 0.0446 moles of a gas. And we're going to use water. So if we go to our problem, let's solve the van der Waals pressure. So we go and we say, well, my pressure is going to be, I'm going to have some moles, 0.0446 mole squared. The A value for water, 5.46 atmospheres, liters squared, mole squared, divided by the volume of the container, 1 liter squared. All that times the volume of the container, 1 liter minus 0.0446 mole, times B for water, 0.0305 liter per mole. All of that has to equal 0.0446 mole. Our R value of 0.08206 atmospheres, liters, mole Kelvin, and our temperature, 273 Kelvin. Let's clean up our sides a little bit. This will equal 0.9991. The moles will cancel, kelvins will cancel. This will be in atmosphere liters. As to our other side, we'll end up with 1 liter minus 0.00136. The moles will cancel, so it'll just be liters on this component, which means really this comes out at 0.99864 liter. And to our pressure component, we'll find that the pressure plus 0.010861, and if we look at units, moles squared will cancel moles squared, liters squared will cancel liter squares, atmospheres. Multiply these together, 0.99864 liters times pressure plus 0.010846 liters times atmospheres. So we multiplied our liter by both parts. All that must equal 0.9991 atmosphere liters. We can subtract this part from both. We'll find that 0.9883 atmosphere liters is equal to 0.9986 liters times our pressure. So divide by those liters on each side. And we can find our pressure. So we can find our pressure if we had done the van der Waals. If instead we had compared this to the ideal gas law, pressure volume equals nRT, so our pressure would equal 0.0446, 0.08206, 273, 1. We would have calculated it out at 0.9991 atmospheres. So at first, it doesn't look all that different. We're only off by 0.01, but that's 1%. And this is when our pressure is low. If you're at the 100 atmosphere level, a 300 atmosphere level, if you have very high pressures, this becomes significant. And so regular gases at Earth-based pressures and temperatures, the difference from the ideal gas law is maybe 1%. But for very compressed systems, where the gases just start to lose the space between them, this becomes a significantly greater problem. So here's an example of a real gas on why we can use the ideal gas law even though it doesn't technically represent what the real pressure is supposed to be. It is a very close approximation at standard pressures and temperatures on Earth.